Hello there, guys. Hello, everybody. And good evening, or shall I say good morning, if you're here in Australia and it's morning and it's past 12. Um, yeah, I hope you guys are having a wonderful day so far. And, I hope that everything is well. Now, today I did promise a bit of a coding stream yesterday, actually. Not even yesterday, the day before yesterday. I promised a coding stream, but of course that did not happen. And I do apologize for that. I'm very bad when it comes to keeping schedules like that because there's so many things that happen all at once. And today, just as usual, before we continue, remember, so I can't have any lo-fi music at the moment. I've paused the stream, so you guys put on your own lo-fi. I've got my own lo-fi here as well from Lo-Fi Go. And yeah, if you guys like that stuff, you guys just put it on yourselves and enjoy while we code and continue to learn about AI stuff as well. So last time we were, unfortunately, I haven't, oops, what's going on here? I haven't caught up fully, but what happened last time was that we were doing this. Let me get everything up real quick. So this is positional embeddings. So I'm a bit confused with this. So basically, um, I'll explain it here. Basically, so Fox jumps over Fox. Is basically positional embeddings where it is inside of the what's called inside of the sentence. So it is a bit of a context in the dimensional space of the tensor, right? So it's just these are basically like the vectors. Then we're just changing the vectors by putting in the positional embeddings. At the moment, that's a bit difficult to understand. Even I'm having issues myself just understanding it, seeing if we're having, where are we putting 2.1, 2.2, 2.3, for example, positional embeddings and, input embeddings, because actually there may be, for example, what I'm thinking, maybe this is just my thoughts on it, is that we have the token embeddings, right? So we have the token embeddings, but what makes it different, I guess, with the thingy, I don't know, it's a bit hard to explain. So basically, it's gonna have two different values, positional and token. Actually, sorry. Sorry, my mistake. No, so I've just got it now. It's just clicked in. No, it's just clicked in. Okay, so I feel like, from my understanding, the same embedding vectors, aka the token embeddings, are the same. Positional embeddings, however, are dependent, of course, on a specific mathematical formula of where everything is. And then using this plus this, we get the basically the next word, or we get the input embeddings of where everything is. So yeah, that's, well, this is 2 a.m. Gabriel here from my uni days, and that checks out. Actually, that logic checks out. That understanding checks out. All right. So instead of focusing on the absolute position of a token, yes, the emphasis of relative position embedding to relative position or distance between tokens. This means the model learns how far apart they are at which exact position. Yeah, the advantage here is the model can generalize better to sequences varying of length. So this is, for example, context length, I'm guessing. Has in such length string trading, yes, both types of positional embeddings aim to augment the capacity of LLMs to understand the order and relation between tokens, showing more accurate and context-aware predictions. Yeah, so context-aware, so basically understanding what is previously said. And Truth also depends on the specific application and nature of the data being processed. OpenAI's GPT models are absolute positional embeddings that are optimized during the training process of it being fixed. Use absolute positional, okay. Predefine likely positional encodings in the original transformer model. This part of the model training itself. It's create initial positional embedding to create the LLM inputs. Alright, so here we go. So, previously we've got some very small embedding size for similar. Now let's consider the more realistic useful embedding size and code. The inputs are going into a 256 dimensional vector representation, which is smaller than the original GPT-3 model used. Yes, very much so, but still reasonable for experimentation. So we assume that the token ID we created, but one thing I need to just run everything in all. Make sure that's all good. Okay. And then put this in. Okay, BP cycle thermal, we assume by the BP cycle implemented, which has a killer of that much. Okay. Code this run. Using the previous token embedding layer. Embedding the vocab, okay. If we sample data from the data loader, we embedded each token in each batch into the vector. If we have batch size of 8 with 4 tokens each, hold on, batch size of 8. So 8 positional, sorry, not 8 part of the vector with 4 tokens each. Wait, no. Yeah, 8. So 8 and a batch of 8. So we're doing it by 8 and 4 times where each token is 256. Yeah, tensor. Let's initiate the data loader. Cool. So let's see, data loader. We're creating data loader version 1. Data input. Oh, good. Yes, so batch size of 8, so 1, 2, 3, 4, 5, 6, 7, 8. 4 tokens. 4 tokens each. So each one has 4 tokens inside them. So token number 40, 3, 6, 7, and all that. And then those relate to a 256 what's called dimensional vector of the thingy. So input shape. So yeah, it's 8 by 4. As you can see, the token tensor array is 8 by 4 dimensional, meaning that the batch consists of 8 text samples with 4 tokens each. Yes, I get now. 8 text samples. So I love you. Yeah, or something like that. Let's eat hot dogs. Let's use the embedding layer to embed these tokens into the 256 vectors. So now we're gonna actually embed it into 256 vector. And then print torch size. So now token embedding layer. So if we look at the embedding layer here, so this embedding layer, right, is just empty. Basically we don't know what it is. So if we do, for example, if we do this, if we do print embedding, token embedding layer. If we do this, maybe not. Maybe I shouldn't print it. Maybe it's not a good idea to print it. Let's hold up on that. Oh, what's going on? Interrupt, maybe? Interrupt. Maybe we should print the token shape. Yeah. Print dot shape. Okay, this is not good. Restart. Okay, now that's good. So let's quickly load everything up there. Okay, now this one. Embedding object has an attribute shape. What do we do then? How to print out the size? How to print size of embedding layer torch? Torch. Let's see. How to do that? So dot weight dot size. Okay. Dot weight dot size. Okay. No, that doesn't work. No, that's different. How to get embedding. Dot weight dot shape. Maybe. There we go. So yes, dot weight dot shape. So now we have the shape of the tensor, right? Which is this much by this much. And then this is just empty. So if we do print token embedding layer, let's say 0 and 0. So we're gonna do 0, 0, and 0, 0. See what that gets. It's not subscriptable. What does that mean? Zoo. I gotta wait. So there we go. Okay, so at the moment it's just, I believe this is using one of the techniques where it is a random embedding vector, right? So this is where it's just all of it. So it's just vocab size of the whole 50,000 something. That's what it is right there. And it's just all random numbers because this is one of the what's it called now? Techniques to do it. Well, what technique it was, but it was one of the techniques. Okay, so we got that shape now. So now what we're gonna do is that we so this will change by training from what I've heard by Gemini. So this is gonna change by training. So it's one of the things. And then we've got the shape here, and now let's see. Context. Okay. The dimensional tensor output shows that each chicken is now embedded. Yes. For GPT's model embedding, we just need to create another embedding layer that has the same embedding dimensions as token embedding. Wait. So absolute embedding approach. We need to create another embedding layer that has the same embedding dimensions as a token embedding layer. So context length equals max length. Okay. Yes, so context length. So this is what this looks like that is going to do here is that the context length is going to be the max length, where that is going to be the full length of the embedding, so that we are obtaining the entire length of the what's called now conversation as whatever it is that we can use to understand the context of the conversation. Of course, this would be limited to RAM and all that sort of stuff. This would be the output dimensions, and then this is the positional embedding. Sorry, this is the positional embedding layer. This is the positional embedding. So torch.arrange, what is that? Hold on, what is torch.arrange? one-dimensional tensor containing a sequence of evenly spaced integers from 0 up to not including the context length of range. Okay, but I have the sensor ready for GPU acceleration. Here it breaks down. So 5. Oh, okay, gotcha. So this is basically a sorting function, I think. No, 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 it's not a sorting function. No. So it generates a sequence of evenly spaced integers. So this is 0 all the way to the context length, and that is creating the positional embedding layer, so that each and every single embedding has a positional embedding as well. And if you print the shape, it'll be the same. Max length is not defined. What did I do? Touch match max length. Let me search up the GitHub. Where is it? Oh no. Where did I put the thing? Is it the test? No, it's not. Oh shoot, where did I put the thing? Hold on guys, I'm just trying to find the what's it called now? The repository for the thingy-majiggy. Repository show in Explorer. I'm certain I've got it downloaded here. How did I? Maybe I don't. Maybe I don't have it here. Yeah, okay, I need to download it. Let me download it. That's build a large language model. It's called LLMs from scratch. Do I have that? LLMs. I do. Okay. Show in Explorer. Open in Visual Code. Yes. Okay. Up. Oh no. Okay. Chapter, what is this? I'm gonna copy this and see if we can find it. No, context length equals. No. Okay. Right. Encoder, is it the GPT? No. BPE, no, not the TikTok one. Embeddings, here we go. Embedding different, no, not that one. Not that one, not that one. Where is it? It's past that one, and maybe it isn't this one. Hold on. Use n dot embedding. Oh, they've got even more detailed stuff on the GitHub there as well. That's amazing. So. No, that's not the one. I think this is BPE from scratch by the looks of it. This is the bonus data loader? No. Yeah, not that one. Python coding from scratch. Here we go. Let's see. Did I do this properly? Russian free, concrete example, BPE encoding. No, not that one. Not that one either. Is it bytepad encoding or where is this? Where am I right now? 2.8. I'm not in chapter 3 yet. Tokenizer, no, not this. Well, it's gotta be chapter 3. Main. Chapter 3 IPYNB, torch version torch. No. Sorry guys, I'm just trying to find, wait, different parts of self-attention without trainable weights. No, this is completely different. No. It's definitely in here. Where is it? Hold on. Tempted to control F. No results. That's not good. Where is the code thing? Did I miss something? Hold on. Maybe I missed something in the thing. The reason that max length is not defined. Okay, so wait, we did. Okay. Yeah, we go. I don't know what happened there. All right. And it says here, as we can see, the positional embedding tends to consist of 4 256 vectors. Now we can add these directly to the token embeddings, where Pytorch will add the 4 by 256 post positional embeddings, which is this one, to each of the dimensional token embeddings. So the normal token embeddings in each of the 8 batches. Okay. This. Oh, wait. I think I'm starting to get it now as to why it's not losing the information. Because when you look over here, you have to remember that token embeddings and position embeddings, they are tensors of themselves. And we're just adding the tensors together. And it's an entirely new, we're adding a new dimension to it as well. So that's where it's not losing information actually. Even though we're combining the things, it's not losing information. So I guess when you do the maths on this, you're working with the whole thing, so there shouldn't be any issues at all. The input embeddings we created as summarized in figure 2.19 are the embedded input examples can now be processed by the main LLM modules, which we will be implementing in the next chapter. It's got input here, so got the main information here. So this is an example. This is an example. It goes to the token IDs, and then it goes to the token embeddings, right? So the token embeddings of where each word is in relation to each other word, and then the positional embeddings, which is where it is basically the position of the word in relation to the context, which is the entire sentence there. And then when you plus it, you put into the input embeddings, right? So it understands what each word is, and then the GPT like decoder only transformer, processing steps, and output text. Okay. As part of the input first break it down up with individual tokens. These tokens are then converted to into token that is using a vocabulary. Yes, we've done that. Token already converted into the embedding vectors, which positional embeddings of a similar size are added. Yes, so it's gotta be similar size as well. Or there'll be some sort of misshaped tensor resulting in input embeddings that are used as an input of the main LLM layers. Wonderful. Elements require, so summary, elements require textual data to be converted to numerical vectors, yes, known as embeddings. They can process raw text. Embedding transforms discrete things like words or images into continuous vector spaces, making them compatible with neural network operations. As the first steps, raw text broken into tokens, which can be word to characters, and a token to convert into integer representations, term token IDs. Yep, and I understand that. And special tokens such as the unknown, which we're not going to be using, and the NF text or EOF can be added to enhance the model's understanding and handle various contexts such as unknown words or making the boundary between marking the boundary between unrelated text. Okay. Oh, there's still some more information here. And the byte pair encoding. Got what byte pair encoding was. Let me just get the quick summary. What is byte pair encoding? I forgot the name. I forgot the idea of behind byte pair encoding. Byte pair encoding, modern. Okay, gotcha. Tokenized, yes. So okay. Yes, so byte pair encoding is just where it's just the handling for the new words out of vocabulary words by separating into even smaller things, and then we can use the positional vectors as well. Add understanding to that. And then let's see. So we sliding window approach on tokenized data to generate input target pairs. Yep. And embedding layers in PyTorch function as lookup operation, retrieving vectors. Representation of tokens, which is crucial to training deep learning modules, and while token embeddings provide consistent vector representation for each token, they like sense of in the sequence, which is what is positional embedding is for. Yes. Two types of embedding, absolute or relative. OpenAI uses absolute, which are added to token embeddings and optimized during the model training. All right, so now we go on to chapter 3, coding attention mechanisms. So we are now on page 50 out of 370. We're like not halfway there, but you know, we're getting there, guys. We're getting there. And this one, integral attention mechanism in isolation. Focus on the mechanistic level, and we'll cut the remaining. All right, so. Stage 1, data preparation and sampling, and stage 2. So we did the data preparation and sampling, which was stage 1. Now we're doing the attention mechanism of building an LLM. simplified self-attention with trainable weights that form the basis of mechanisms using LLMs. The type of self-attention using LLMs that allow a model to consider only previous and current inputs of sequence during temporal order, during the text generation, which is casual attention and multi-head attention. An extension of self-attention and casual attention that enables the model to seamlessly attend to information from different ranges subspaces. The figure depicts different attention mechanisms will occur in this chapter, starting with a simplified version of self-attention before adding trainable weights. The casual attention mechanisms adds a mask to self-attention allows down to generate one word at a time. Finally, multi-head attention organizes the attention mechanisms in multiple heads, allowing the model to capture various aspects of the input data in parallel. Arrive at a compact and efficient implementation of them that we can then plug into the LLM architecture. Yes, okay. LLM architecture being like if it's Llama or GPT, all that sort of stuff. Or Mistral and all that sort of stuff, which I've actually never covered in university. So this is all new stuff in terms of the actual thingy architecture type. I don't think we covered that. Before we deep dive into self-attention, that do not include attention. Language that translate text from word. We can't sometimes translate text from word by due to grammatical structures in the thing. Can you me help this sentence to translate? The word by word, yeah, grammatically incorrect. An encoder and decoder. Alright, so the job of the encoder first read in, process the entire text. The decoder then produces the translated text. Alright. Now, I did learn a bit about RRNs and CNNs and all that sort of stuff. So, most popular encoder decoder architecture for language translation. Serial type outputs from previous steps are fed its inputs to the current step, making it well suited for sequential data like text. I think this is one general concept of encoder decoders. Okay. And input fields. Input text is fed into the encoder, which processes it sequentially. The encoder updates its hidden state, internal values hidden layer at each step. I'm trying to capture the meaning of the hidden state. The decoder takes this final state to start generating the translated sentence. Hold on. The decoder then takes this final hidden state to start generating the translated sentence one word at a time. It also updates its hidden state at each step, which is supposed to carry the next necessary forward next word prediction. Alright, Gemini, explain to me what is a hidden state. Oh. Right. Okay. Yeah, Gemini's broken. Gemini's broken. Gemini's gonked, man. Explain to me what a hidden state is in AI context. Oh, well, that makes sense. So basically, it says here in context of AI, think of it as an internal working memory or short-term scratchpad. So basically, it's just variables that's currently being used. So yeah, memory cell. Okay, that makes sense now. That changes with every new input. It's called hidden because this it's called the hidden simply because it sits in the middle layers of the new. Oh my gosh, are you serious? Is this why it's called hidden? But hidden states an internal calculations happening behind the scenes. Dude, I thought like, man, I thought it's completely different. I thought it was something. No, never mind, never mind. Anyways, alrighty. I gotta. Well, but no, then just grab a drink real quick. Alrighty. Cool, cool, cool. Okay, so uh so we are talking about the attention mechanisms. So basically, in terms of the hidden layers, they can actually lose focus or lose understanding, depending on how large the hidden layer is. So I'm guessing. So we need the attention mechanisms. They go apparently by according to Gemini, they go through the entire list of hidden states at once to better understand all of the context or information to prevent information loss. I believe. Let's see. Oh yeah, it thinks it as an embedding vector as well. Yeah. Uh, yeah, this one. Yeah, so Gemini was right. Explain later because I went too far ahead with Gemini. Um, mm, mm, mm. Of attention mechanisms. Yep. Um, Single hidden state before passing into the decoder. Hence, researchers developed the Danu attention mechanism for RNNs. Same first of the respective paper formed the decay. Hold on, my glasses. Hmm. And later on, we're gonna learn about a thing called quantization aware training guides, which is what Gemma is doing. So Gemma by Google, which I didn't even know was a thing. Quantization aware learning. What in the world is that? Anyways, okay. Kannst du mir so the dotted line width is proportional to how important the input token is for this. Okay, so this is very important. So can not important. U is very important. See all the hidden states go to there, and we're focusing on generating the second output token. So okay, so this one grabs one token. This is the embedding one. So think of it as embedding, right? So basically, cons is like maybe 1 2 3 4. Do is 7 6 1, and then that goes into the hidden state, which then the decoder uses, I guess, with a lookup table, something of that sort. And then to mir. Are you sure mir is, what is mir? Mir from German to English. No, isn't it helfen? Yeah. Can you? Yeah. When joining an output token, the model has a way to access all input tokens. Okay. Sorry, I just gotta blow my nose real quick, guys. All right. The tech generator part of it can access all inputs selectively. This means that some more important than others for generating a given output token. Okay, the important statement by the attention weights. Okay, so the attention weights. This is, yeah, okay. So this is basically if you, for example, had a birthday, you're going to remember the birthday more or the happy moments more than you are going to, remember what you ate for breakfast, essentially. Yeah. Which will compute later. Not this figure shows a general idea, but does not depict the exact information of the bundle mechanism, which is outside of the book scope. Okay. Gotcha. Don't worry. Interesting. Only 3 years later, research found that not required for building the model for natural language processing and proposed the original transform architecture, including self-attending. Self-attending allows each potential input signal to consider the relevancy of or attend to all other petitions of the same signal in computing and representation of sequence. Self-attention is a key component of contemporary based on a transformer architects such as GPT series. This series focuses on coding and understanding the self-attending using GPT-like models. As next year, will code the remaining parts of the LLM. Wonderful. Okay, so let's see what this is. Topic of the previous chapter. Yes, topic of the current chapter. GPT-like decoder only transformer. Self-attention. The remaining parts of the architecture are the topic of the next chapter. Okay. Gotcha. Go. 3.3. Attending to different parts of the input with self-attention. We'll now cover the inner workings of self-attention mechanism and how to code it from the ground up. Awesome. I love that. Self-attention serves as a cornerstone of LLM based on the transform architecture. This simple may require a lot of focus and attention. No. Oh my god. I see it now. Wow. Great job. I would not have realized that if you did not point that out, but okay. Once you grasp the fundamental, you have conquered one of the toughest aspects of this book. Yes, and LLM implementation in general. Okay. All right. The self in self-attention. A self-attention mechanism is compute attention weights by relating different positions within a single input sentences and learns what the relationship dependencies between various parts of the input itself, such as words in a sentence or pixels in an image. Yes, such as the difference between Chihuahua and a blueberry muffin, if you guys haven't seen that yet. And is the contrast to traditional attention mechanisms, where we focus on the relationships between the elements of two different sequences, such as the sequence to sequence models, where the attention might be between an input sequence and an output sequence, as they're depicted in figure 3.5. All right, so seeing self-attention can be complex, especially if you're encountering it for the first time. We'll begin by examining a smaller version, but then we'll implement self-attention with trainable weights using LLMs. Cool. All right, so yeah, this is the this is, by the looks of it here, the positional. This is how we obtain the positional thingy, positional vectors, positional embedding. Sorry. Okay, so input vector token embedding. Oh, sorry, no, this is token embedding. Corresponding to the first token, so this corresponds to your and then all that. Attention weight to weigh the importance of the input. So, for example, journey. Start is going to be more important, I guess. And then the context vector. Z is computed as a combination of all input vectors weighed with respect to the input elements X. Hold on. Wait. Okay. So let me get this right. Okay, so attention weight to weigh the importance of the input. So alpha 21 input X over 1, or X1 basically. And then the context vector, right, which is Z2, is the computed combination of all input vectors weighted with respect to the input elements 2. So this one would be input element 1, this one would be input element 2, and this one would be input element 3. Oh no, sorry, because this is Z1, I'm guessing, right? So, actually, is this 0.4 in relation to this one, or no, this is a context vector, so this is itself like a tensor by itself. Yeah, so it is a vector of 1 by 3. All right. So, but this is the context vector of all of everything combined in relation to X squared context. So X2 context is Z2. Okay. The goal of self is to compute the context vector for each input from the combined information from all other input elements. In this context, we compute the context vector Z. Yes, the importance or contribution of each element for computing Z is determined by the attention weights. A1 to A2. When computing Z, the attention weight is called with respect to the input elements X2 and all other inputs. So, that's a bit tricky. Oh no, it's a wall of text. Hold on, guys. I gotta put this again. Sorry. Be right back. Hold on. I just realized, are you guys not able to see that? Let's see. Oh my gosh, I'm so sorry you guys weren't able to see that. I'm so sorry, guys. Boom, boom, boom. Okay, there you guys. Okay, guys, go now. Now you can see it. Yay. You guys can actually see what I'm reading and understand on the way with me. Alright, so figure 3.7 shows an input sequence. Yes, denoted as x. Yes, considering of t elements, depending t is like n, the number of elements, sentence x at t. Sequence typically represents sex, that says, or being, or in this case, token. Has already been transformed into a token. Embeddings. Yes, for example, consider the input your journey set in this element such as x1 corresponds to a d-dimensional embedding represents like specifically like your okay. This as three-dimensional embeddings. Yes. In self-attention algorithms to calculate context vectors for each element. So context can be entered as an enriched embedding vector. Okay, gotcha. Seems more like the input vector, something like after you do the positional embedding, I guess. To illustrate the concept, let's focus on embedding vector of the current input element and the corresponding context. Z2 from the bottom of figure 3.7. This chance context vector. Yes, Z2 is an embedding vector that contains information about X2, which is journey, and all other input elements. So X2 in relation to its standing to all the other words in the sequence, or in this case, the context, or basically the sentence. If we were to use a sentence as an example in this case, because we did use your journey starts with one step. So by the looks of it here, it is the contain information about journey in relation to in relation to everything, including the journey, which is weird. I don't know. The math checks out, I guess. I guess the math checks out. Yeah. Let's see. So let's focus on an embedding vector or the second input element, which comes into the token journey and the corresponding context. Oh wait, no, we already read that. Coding vectors plays a crucial role in self-attention. The purpose is to create enriched representations of each element in an input sequence, like a sentence. Yay! By incorporating information from all other elements in the sequence, this essential element LLMs which need to understand the relation of relevant words in the sequence and other. Later, we'll add trainable weights that help construct these context vectors so they will so they are relevant for the LLM to generate the next token, which I guess saves space as well. Let's implement a simplified one of the self attention compute to compute these weights and the resulting context vector one step at a time. Consider the following input sequence, which have already been embedded into three-dimensional vectors. I've chosen a small embedding dimension to ensure it fits the page without line breaks. Thank you. So let's grab this. We're gonna quickly go here. I'm going to do this and go rename. We're gonna call it main practice chapter 2, and I'm gonna grab a new one to main practice chapter 3, the IPYNB. And let's do this import torch, but I'll show where is my thing. Oh, the rule lib. Where is my thing? Did I import torch again? No, I think we imported torch last time. Did I? We did. No, you know, I don't think I should do anything. I think cancel this. I'm gonna cancel this. I'm just gonna go up with you. Actually, I should probably make a new one. Yeah, let's just go here. Port torch. Rock M. But we're gonna quickly grab this. Where did I put the thing. Where did I put a thingy here. That basically, where is it? Where is it? Where are you, Butterball? Here we go. It's CUDA support. The CUDA support tracker. Huzzah! So, CUDA support tracker. What's this? CUDA support tracker. CUDA support true. CUDA version none. 9070. PyTorch now using CUDA. Awesome. Let's go. Alright. So, first up, implementing software into computer intermediate values. Weird math symbol there. Referred to as attention scores as illustrated in 3.8. Choose two spatial controls to figure out values. In the truncated version example, 0.87 is truncated to 0.8. Where is that? Wait. Due to special constraint, the figure displays the values of the preceding input sections in the truncated version. Ah, okay, gotcha. In this version, the embedding event may appear similar. Embeddings of the words journey and start. Where is that? Journey and start may appear similar by random chance. Okay, gotcha. So, fifth page 58. So we went from page 40. I went from page 43 to page 58. The whole 10 pages. I'm very good. I need more water. Be right back, guys. BRB. I'm back. And I'm tired as well. It is almost 3 in the morning. You can tell I'm pretty tired. But we continue. We've been at it for 1 hour. Oh boy. 1 hour learning tough concepts and topics. I like that. I think. I don't know. Do I like it? Or am I just forcing myself to do it because I need to? I don't know. I like it actually. Alright, let's see now. Alright, so now we're talking about the weights, I guess. Or the attention score, sorry. The embedded query token is that. Shared query is the second. Hold on, so the embedded query token is one of the. Wait. Huh? Embedded query token. So we're talking about the word your inputs. So 0.9 attention score between input. Okay. I get you. Attention score between input 2 input 1 and the word and the token. This one. Yeah, so this is the embedded token thing. I get you. So that's why I made, Miller. Because it's been done for that. And you get weights 1, 2, 3, and all that stuff. The level goes to illustrate the computation between the vector z2 or z2. I don't see z2. Or maybe what it means is z2 in previous, which was this one, which is currently these ones. Or z. Don't know. There's no z2 here. Using the input element x2. First intermediate step, computing the tangent scores between the first w and w this. Computing this as a dots product. Oh no, shrunken it to 1 digits after that. Okay, so we're doing a dot product. But how do dot product, guys? Hold on. Dots products formula. Formula. I was good at dot products, but I forgot how to do it. Dot products formula. Oh gosh. Dot products. A1 plus. Oh wait, is that it? I'm just dumb. No, that's it. Yeah. So we're not talking all vectors right now. Yeah, but yeah, that dot product is basically the addition. No, dot product is the sum of everything. Okay, gotcha. So that's the dot product again. So only one is a yeah. Gotcha. It is why I need a refresher, man. Every time we go through these complex topics and all of that sort of stuff. Oh no, I need to pull one of those again. It's winter, guys. BRB. All right. Okay, so let's calculate the changes within each query token and each input token we determine. This goes by computing the dot product of the query with every other input token. So basically, embedded query, so 2.1. So 0.5 plus 0.4, 0.8, sorry, no, sorry. 0.5 times 0.4. Let me get the calculator out. Actually, let me get Wolfram Alpha, my favorite buddy. 0.5 multiplied by, give me a minute, guys. 0.5, 0.5, 0.8. Let me just make sure I got everything correct. 0.6, 0.6 dot 0.5, sorry, 0.5 times 0.4 plus, and then this is gonna be 0.8 times 0.1 plus 0.6 times 0.8. Wait, why is it different? Huh? Did I do something wrong? Let me just make sure I got. That can't be the dot. Why is the dot product different? Why is that different? That's weird. Dot products of 0.5, 0.8. That's weird. 2.6. Then 0.4, 0.1, 0.8. 0.76. Huh? Let's see. Dot product of itself then. 0.5, 0.8, 0.6. 1.2. Why is it different? Something. This is not the real dot products. I'm putting this through Wolfram Alpha, and I did a manual calculation as well. This is. There's something else that's going on here. So. We're gonna need to look into this. Something else going on around here. That should be the attention score, right? And it mentioned it was the dot product, so unless I'm missing something that I'm not aware of. Okay. Computing the dot product of x2 with every other input token. Yes. Yes, I've done that. Unless I know I didn't do anything differently. No, that's it. Like I don't. So computer attention scores are. Something is weird here. Oh wait, no, I get you. I get you. You guys want to know why? Because this is the shortened version. So it's actually 0. So let me just. I forgot, man. I forgot. This is why. If I do dot product of that with that, when we use the actual values to the second decimal place, then it should. If we do dot product like that, it then should. Come on, Wolfram. Come on, Wolfram Alpha. You can calculate it. Come on, work with me. Yeah, 0.9. Yeah, it's been rounded. Yeah, it's just been rounded down and all that sort of stuff. So, yeah, 0.9544 it is indeed. So this is the actual dot product. Yeah, it's just decimal place stuff. Oh, whoopsie. So let's copy this. Let's put it into the code. Which, if it's dot product, that's pretty easy. But it's got its own thing though, so that's pretty good. It's got its own thing, and using tensor. Oh, sorry, not tensor. It's using CUDA. Yeah, so that's pretty good. This is where CUDA comes into play. Are we using CUDA now? Let's see. I want to see my GPU when I use this. I don't know. I don't see any. I don't see any change. Okay, but yes, the thing is correct. Understanding dot products. Good thing I took maths. And good thing maths was a required thing, even though it was so painful. Oh my gosh, you guys have no idea the amount of pain maths brought, man. It was intense. It was hard, but luckily, in the end of the day, I got a really good teacher who just really wanted to help me, and I was able to understand it. She was very, very helpful. I can't thank her enough, man. She was just so understanding, just so helpful with everything. Best math teacher. Concise way of multiplying two vectors element wise. Yes, then summing the products should be yes, times This app confirms, gives the same. Got that. Cool. Awesome. So torch dot, and then that one is just the thingamajiggy. But what is it? Dotting. So sorry, inputs dot shape. Wait, like query, and then turn the x 1. I guess for the amount of inputs, you just do that. Torch dot inputs. Yeah, it's one of the thingy majiggies. Enumerate over input. So however many inputs there are, right? So there's like, 1, 2, 3. So all the inputs enumerates it for I, and everything else. That's what it goes with. Cool. So that's all calculated there, and then beyond viewing the dot product operation as a mathematical tool that combines two vectors, so the dot product is a measure of similarity because it quantifies how closely two vectors are aligned. How the product indicates a greater degree of alignment, okay, or similarity between the vectors. In the context of self-attention mechanism, the dot product determines the extent to which each element in a sequence focuses or attends to any other element. The higher the dot product, the higher the similarity and the attention score between two elements. Okay. I don't know what the limit is on that, but alright. The next step, shown in 3.9, we normalize each of the attention scores we computed previously. The main goal behind a normalization is to obtain attention weights that sum up to 1. This normalization is convention that is useful for interpretation and maintaining the training stability in LLM. Here's a straightforward method of achieving the normalization step. So yeah, it's just, by the looks of it here, it's just the sum, or the average, I guess, something of that sort. Sum tensor attraction weight, sum tensor 1.0. So, but oh no, I get you. So basically, we're getting the attention score, right? Dividing it by the amount of how many there is, and then that's where we got that. And then when we sum it all up, it'll equal to 1. So everything is in relation to 1. So that makes sense. We computed these in the previous step, yes, and then the attention weight. So okay, so attention scores is the raw thing without normalization, right? So it can be like 2 point something, all that stuff, like 1.4, 1.4, and then attention weights. So this is the weights, is where we can normalize the attention. Where we have normalized the attention score to attain the weights. So I'm guessing when people talk about weights, this is it. This is what the weights are, open weights. I don't really understand how weights exactly can be useful at the moment, because there's so many, weights can be useful, but there's just so many weights in a model. I don't know what sort of automation process or whatever it is people usually use. Goes with respect to the query X. The next step is obtaining weights alpha 21 to 1 to alpha 2t by norming the attention scores. Done. Awesome. You know what? This actually makes a lot of sense, and I'm so glad I'm reading through this, man. We now get the sum of that. In practice, more common and advisable to use the softmax function for normalization. Yes, managing extreme values and offer more favorable. So softmax. Gotcha. So yeah, normalization, softmax. So that's what they mean. The thing is, like, this sort of stuff, attention, the weight stuff was told by us, but the actual it was taught to me in university. But we just covered the basics. They didn't tell us, and it didn't make really much sense as how weights came to be, I guess, in terms of mathematically. But now that we know that, hey, it is actually the dot products of the context, right? So, you know, x2 in relation to everything, and then we normalize it. That's how we get the weights. And then we use the softmax function, which is basically a mathematical function to normalize things. So that's how we get it. That makes a whole lot more sense now, and it just clears my mind, man. It just clears my mind. All right, softmax function, basic component of softmax function for normalizing attention scores. Softmax 5. 1 point that. Okay. So the softmax function is, I guess, by the looks of it here, better as well. Alright. I guess it's why you may have different weights. So if you were to, unfortunately, then you can only use one type of normalization function. Otherwise, you're gonna get completely different weights and completely different context understanding of each token. Wouldn't be good. Wouldn't be good at all. Okay. As output shows, softmax function only to normalize the weights by the sum of 1. Yes. In addition, some assume the intentions are always positive. Okay, yeah, that's right. This makes the output interpretable as probability of relative importance where higher weights indicate greater importance. Yep. So 0 to 1, the naive softmax function. So may encounter numerical instability such as overflow and underflow when dealing with large or small input values. Therefore, in practice, it's well to use the PyTorch implementation of softmax, which has been extensively optimized for performance. Don't create your own ones, guys. Just use the PyTorch. It's there for performance. Dimension 0. I don't know what dimension. Oh, I don't know what dimension 0 is. But there we go. Oh wait, yeah, I know. Sorry, one dimension is like wing, like a line. Yeah, gotcha. Let's go. It's the same results. Now we have computed and normalized attention weights. We are ready for the final step. As shown in 3.10, calling the context vector by multiplying the embedded. Multiplying. Where? 3.10. Let me go back to that. 3.10. Is this 3.10? No, where's 3.10? Wait, I didn't see 3.10. Oh, 3.10 is here. Okay. Sorry, my mistake. Ready for the final step as shown in 3.10, calling the context vector by multiplying the embedded input tokens with the corresponding attention weights, and then summining the resulting vector. Thus, the context vector Z2 is the weighted sum of all input vectors. Okay, so hold on. We're going to calculate the context vector, right, by multiplying the embedded input tokens, right, which is the embedding layer, with the weights. So this is where we've calculated that specific input token in relation to the whole context. So the whole sentence, for example, in this case, right? And that is where we will then obtain the context vector. Yep. Thus the context vector is the weighted sum of all vectors obtained by multiplying each vector by its corresponding attention weights. So input token is a query. Yes, so journey is the query here in this case. So if we go here, so it's got 0 point this. Yep. And yeah, as you can see, so this is multiply, then add. So multiplying each vector with here, and then this is second context vector becomes the attention weight. Okay, sorry. So multiply each vector, so 0 0.1, and then plusing it also 0 0.1 plus 0 0.2 plus 0 0.2 plus 0 0.1, which is 0 0.2, 0 0.4, 0 0.6, which is this 0 0.6. This is the second context vector because the attention weights were computed with respect to the second input vector in the previous step. The final step after calculating and normalizing the attention scores to obtain the attention weights for query X2 is to compute the context vector. And the final step of analyzing attention scores to obtain the attention weights for query X. Compute. Wait. No, sorry. These are attention weights. Wait. Didn't we already do that? Hold on. What? I'm confused. Hold on. I'm not really confused. I'm just wondering. Sorry, my apologies. Let's see now. All right, so final step, right? After calculating and normalizing the attention score. So we've calculated it first, and then we've normalized the attention weights. So we've normalized the attention scores to obtain the attention weight, which is this one. Oh, okay. Okay, it's just an English thing. This context vector is a combination of all input vectors. Yes, weighted by the attention weights. Next, we generalize the procedure for computing context vectors to calculate all context vectors simultaneously. Okay. So, computing attention weights for all input vectors. How long is this? 3.32. Hold on, page 61. Oh, wait. How many? Page 61. How many more before we get to... Whoop. It's a lot, guys. It's a lot. Wow, this is a lot of stuff. Wow, that's a lot of stuff. How many? 86, 87? Oh my gosh. 92, 30 more pages. Oh my gosh. Okay, that's gonna take a while. Wow. All right. So let's go back to page 61. I think then in that case, we're going to take it bit by bit. So after this, we're going to go... How far away is it? No, you know what? Okay, we're going to do 3.3.2. This is going to be our last one for today. Because, again, it's quite a lot of... This chapter is long, man. This chapter is super long. Super duper long. So far we've computed attention weights for the context vector for input 2 as shown in the highlighted row. Yes, we have. So Jenny in relation to, well, everything else. Now let's extend its... Sorry. Let's extend its computational calculator for all inputs. Okay, so we're just doing a for loop by the looks of it here. The order as a query. Now we generalize the computation to obtain all other attention weights. Please note the numbers in this figure are truncated into two digits. Yes, the reduce visual clutter. The values should add up to 1.0100%. Okay. So we follow the same 3 steps as before in 3.12, except make a few modifications to compute. Yeah, so to compute all. So it's just we're in. So basically what's happening here is that we're adding an extra what's it called, for loop. So but I and and then for J in the amount of times in inputs. Okay. And then compute the attention scores, compute the attention weights. Wait. One. Oh, like computing the dot product from all the pairs. Okay, they're doing the dot product from all the pairs. So that's what they've changed. Yeah. And then after that, the attention score. Oh shit! No. Okay. I was gonna hoping that would have been bad. All right. So computer has weighted some over the inputs. Okay. Step one, we add an additional foot. That's already done. Gets that, and each element in the tensor represents an attention score between each pair of input, as we saw in 3.11. And now that the values in the figures are normalized, yes, which is why they differ from that in the preceding tensor. We'll take care of them. Okay, we haven't normalized them yet. So when computing the preceding tensor, we use for loops in. Okay, that's why it's so high as well. We'll take care of the normalization later. When computing, we use for loops in Python. Our for loops are generally slow. We can achieve the same results using matrix multiplication. Okay. Well, this is interesting. All right. So here's something that's specifically, I guess, to this. What is this? Inputs. The inputs tensor. Okay. Oh, wait, no, we already know it's a tensor, so. What is that? Matmul. I don't know what that is. Wait, what is going on here? Huh? Wait. Is this just inputs multi dot product inputs transpose, or what's it called inputs that doesn't make sense. What in the world is this doing? This code is in Python. What is it doing? Okay. Deep learning, especially line by line inputs. Yes, so 2D matrix and all that sort of stuff. Oh, okay. So at is actually the official operator for matrix multiplication introduced in 3.5 Python. And T transposes it, so it's flipping the rows and columns, making, yeah, so doing the thing. When you multiply a matrix by certain transpose, you're calculating dot product every single row and every single between every single row and that's actually genius. I didn't realize it like that. But when you think about it, multiplying far out. Hold on. Matrix multiplication. I need to check that out again. I need to make sure I've got the right idea again. A plus. Let me just make sure. A times that plus A times that. Hold on. Matrix multiplication for dot product. Let me see real quick. Just so I get my bearings around this. matrix dot product transpose. Where is one where I can get a transposed thing? Okay, let's. Give me a moment. Transpose. Oh, see the number of characters. Okay. Okay. All right. But basically, if we do multiplicate, if we do the thing, so hold on. Matrix transpose. Let me just quickly have a look just to make sure I got the right idea. Matrix transpose. So ABC, ABC. Okay, so yes, it does make sense. So, all right, yeah. So it is doing each and every single one, but each and every single thing. So, gotcha. So A times A plus, and then B times B, C by C, D multiple. No, what? Hold on. I feel. Hold on. This is. Hold on. I'm just. Dot. No, sorry. This is not the dot product yet. This is just. But this is. Huh? I'm so confused in the maths. I'm so confused in the maths. I don't know. Maybe this is a shortcut. So basically, attention scores, easiest way to do it is just multiplied by the transposed thing. So it does it automatically. You don't need torch dot dot or anything of that sort. It just is that. That's it. Gotcha. All right. It's just a math thing. It's hard at the moment to wrap my brain and head around this because, well, I don't have any sample data that I can use. Anyways, in step 2, figure 3.10 would normalize each row so that the values each sum up to 1. Okay, so attention weights, social summa, extension scores, dimension -1. What does it mean by dimension -1? With PyTorch, what does it mean when dimension equals -1? Let's give it this example. No! Equals -1. Okay. Enter. Go, Gemini, go. When it to be interpreting the dimension. Dim is short for dimension. Means the last. Okay. It tells what to apply the operation along the very last dimension. Wait. The very last dimension. Huh? I don't get this. Okay. Okay. Alright, so each row represents a specific verb by focus. By using dimension 1, you guarantee the word 1, which is can. It's just using can you help in an example here. Gemini has gave me distributes a total budget of 100% attention across all words in the sentence. Okay, dokie. It's probably got something to do with Torch Softmax something. Torch Softmax thing more into the method. It's able to calculate that, which is good that, you know, we have something efficient. Anyways, returns the following that's good. In the context of PyTorch, the dimension parameter in function like Torch Softmax measures the dimension of the input tensor along which the function will be computed. By setting dimension 1, we are instructing Softmax to apply the normalization along the last dimension of the attention scores tensor. If attention scores is a two-dimensional texture, for example, rows, columns, it will normalize across the columns so that the values in each row are summing over the dimensions, sum to 1. We're going to verify that all rows lead to 1. Okay. Create all context vectors via matrix multiplication. Boom. And the resulting tensor, each row contains a three-dimensional context vector. Awesome. So this is attention weights multiplied with the inputs. And then we can double check the code is correct by comparing the second row with the context vector computed in section 1. So if we do this, previous context vector 34419 651 this one. So the attention weights multiplied by the inputs equals all of the context vector. So it is all of the context vector for each and every single one. So I think, what was it that I don't know what it was that we typed up here. Something. Your journey, yeah. So your journey starts here, and then your journey starts something like that. And then based on the result, you can see that the previously calculated context vector 2 matches the second row in the previous tensor exactly. Indeed, it does. This concludes the code walkthrough. So next we will add trainable weights. Okay, so that's what it is. Enabling the LM to learn from data and improve its performance on specific tasks. Okay, so that's why weights are important. All right, gotcha. Okay. So, guys, I think I'm going to end it here. 3.4 is where I'm at right now. And with that, I feel like I'm gonna probably play some games or sleep. I'm gonna take a bit of a break, guys. I'm gonna take a bit of a break. And I'll try to do this next time as well. Anyways, with that, thank you guys so much. I hope you guys have a wonderful rest of your night or day or whatever. And I'll see you guys later once I've taken a bit of a break, you know, because we've learned a lot. An hour and 40 minutes essentially of complex stuff. Yeah, I'll talk to you guys later. Bye bye. Take care. Bye.